All right. Hello, everybody. My name is Jeremy, and today I'll be presenting my workshop one idea. I think it's easiest to start off by kind of having an overview of what my idea is and relaying it to the real world problem before we dive into the code. So, my idea was that it would take a static screen share of a Pokemon game and decide if the Pokemon's accessible or not. So in this situation, the trainer's right here, and the Pokemon, which is Moltres, is right here. And it checks all possible paths, which this is a pretty uninteresting area, but it's hard to find screenshots of these situations. But so it'll check all possible paths. So in this instance, the only path it can go was here. And it sees that Moltres is inaccessible. So it will return false. And in this instance, it checks this path and checks this path and finds that Moltres is accessible from the trainer. So it returns true. So before I go and present my pseudocode, we'll talk about the pre and post conditions here. Counter is being passed into my function and it's set to 1. And N&M must be greater, not bust. N&M must be greater than or equal to 2. So the trainer has space to search the matrix. So it wouldn't make sense if it was a 1-by-1 area because then only the trainer could be there, you know? So imagine this, if it's a 1-by-1 matrix, it's just the trainer staying there. But if it's 2-by-2, Moltres could be right here. The post conditions, it returns true if it finds a path to the Pokemon, or it returns false if there's no Pokemon on the screen or a path to the Pokemon cannot be found. So let's say it takes the first screenshot here. There's no path to the Pokemon, so it returns false. Let's just imagine Moltres isn't even there. It would also return false, obviously, because there's no Pokemon to even have a path to. So we'll exit out of the slideshow here for a second. And I think it's, I kind of want to show off the code that I made too a little bit before I get into the pseudocode, just so you can see how this works. So we'll build and run this, and we'll zoom in and go to the top. It identifies that a Pokemon's in the matrix, so it'll run the test to see if it's accessible. Because if there's no Pokemon in the matrix, there's no reason for it to even run, right? So it starts out, the zeros are the empty paths, like we saw with Moltres, in the Moltres screenshot, I mean. And the walls are just like the walls or the strength boulder. It needs to be moved. And P is the Pokemon here. So I can zoom in even more. And it starts out, goes out 1, 2, 3, starts spreading out throughout all possible paths that it can go, checking everywhere, and incrementing how many steps it's taking to get to the Pokemon. 7, that splits 8 here, 9, 9, 10, 11, 12, and boom, it took 12 steps to get to this Pokemon. And we can also show off the pseudocode here, the global variables that it has to consider, N and M, respectively the amount of rows and columns, the parameters that are being passed into the function. It's passing in the matrix or the screen, and it's passing in the counter, which is just keeps track of how many steps we took to get to the Pokemon. And inside, forgot to include X here, sorry. So we have I, which is used to index through the rows, J, which is used to index through the columns, and X, which is used to stay inside the while loop. So it starts out by initializing X to 1, so we can get into the while loop, and then setting it to 0. And X will be incremented every time the map is updated. And we do that so it stays inside the while loop. At the end, or not at the end, when it resets, it'll set X equal to 0 again. And once it stops updating, that means it hasn't found a Pokemon in the path. And if it does find a Pokemon, it returns true to the function. And if it goes through every instance of I and J, or not even every instance of I and J, and it just can't find a path, it will return false at the end. So the time and space complexity of this, I analyzed that your best case running time will be n times n, and that's actually simplified a little bit because the best case running time would actually be n times 1. But the 1 doesn't really matter that much. And for our worst case running time, we have n squared times n squared because it has to run through the entire matrix an n and an m amount of times. So an example of that would be if the trainer's all the way in the bottom left corner and the Pokemon's all the way in the upper right, and the path is like just going up and down, like snake, like a snake-like pattern. That would be the absolute worst case running time that you could have. That'd be n squared m squared. And the expected running time, it more or less, like, you have it's going to average out to be more of this than n times n. For the splice complexity, we're not using a lot of variables, so it's just 1 across the board. For our loop invariance, we initialize, for the initialization of our 2 for loops, screen I and J are both going to be at 0. Like I and J are both going to be at 0, obviously, because we haven't iterated through the matrix at all yet. And the function will return true if it finds a path to the Pokemon. While you were in the loop, there are unique cells still in the matrix, and find Pokemon has not returned true. I and J must be greater than or equal to 2, but less than n and m respectively. This is the technical way of writing that. And the maintenance of this now. This is a lot, but I mean, as we all know, the loop invariant is just a lot of explaining exactly what's happening. So this actually is not as technically proficient as it looks, but it's essentially saying if it runs through the matrix and finds T initially, then the function checks each direction for T for a Pokemon. And if it doesn't find a Pokemon, then it checks for walls. And if it doesn't find a wall, then it checks for zeros. And if it's a 0, then you walk in that direction. I'm using like air quotes to say walk. And you replace the 0 with the counter to indicate that you took a step. It's like a visualization in the matrix. And once you do that, then instead of searching for T, you search for the counter. So you initially find the trainer, and from the trainer's position, you branch out to all the zeros around the trainer, and you replace those zeros with ones. And then you search the matrix again and find those ones and look around those ones for zeros. And if you find zeros around the ones, then you replace those with 2. And that keeps going until you find a path to the Pokemon. And we exit the loop. Oh, sorry, went to the other one. We exit the loop without returning true. This means we left on the condition that there's no path to the Pokemon from the trainer. I mean, that's true. If we don't find a path to the Pokemon, then there is no path to the Pokemon, you know? That's basically what it's saying. Therefore, it is correct to return false because all paths around the trainer have been checked and none led to a Pokemon. Otherwise, we would have returned true inside the loop upon finding a Pokemon. The second loop invariant, this is for the while loop here. So the first one was for these 2 for loops. The second invariant says for initializing, x is equal to 1, and the function returns true if it finds a path to the Pokemon. While in the loop, it sets x to 0, and there are still unique cells in the matrix, and find Pokemon is not returned true. If for maintaining the loop invariant, if screen ij is updated at 0 or counter, the loop increments x to stay inside and keep searching for a path. And if it cannot update at 0 or counter, the loop does not increment x and breaks out, returning false. And to terminate this loop, if we exit the loop without incrementing x, this means we left on the condition that there's no path to the Pokemon from the trainer. Therefore, it's correct to return false because all paths around the trainer have been checked and none led to a Pokemon. Otherwise, we would have returned true inside the loop upon finding a path. And now that the loop invariants are out of the way, I thought I'd showcase a little more of the program that I made. So we already ran this example in the beginning. So I'll comment that one out. And we'll do a different size matrix. This one's 7 by 4. Or 4 by 7, I mean. So we'll build this one, and you can see the Pokemon's here. The trainer's in the top right. And takes 8 steps to find it. So it starts by branching out and runs through here. It took 8 steps to get to it. And we'll actually change this so there's no Pokemon in the matrix. Just so it shows there's no Pokemon in the matrix. It takes steps all the way through and make sure there's no Pokemon, and there isn't any. So this one's a 5 by 5. This one, it took 4 steps. So here the trainer's in the center and the Pokemon's hidden behind a few walls here. So he goes every direction. 2, 3, 4. And this one actually went to a 5 here. because theoretically could walk that way. But we found the Pokemon here in 4 steps. And last but not least, we'll have a nice 2x2 matrix here. The absolute minimum you can have. It'll only take 1 step to find it, but there you go. Took 1 step. And yeah, that's really all I have, and I hope you all enjoyed. Thank you.